I have to start, although so many people are still not here, but I have to start because we have so much work to do, and we are behind a little bit, so we have to catch up. We have 2 more chapters for next 2 weeks. So because I asked from the other class for a question, somebody asked this question, which I think it will be a good one to discuss it with you as far as the static goes and as far as the tension and compression, which is problem, I believe, 121 and 124, which are on the same nature. However, you have to be very careful. In that problem, I want you to understand what was happening there. There is a part of a beam or whatever, it doesn't matter. The way it was, the problem was given, the cross-section was the rectangular cross-section, so this is the C, but the force was given at this point, P. Is that correct or not? First of all, you have to be very careful about the static. The student have problem with that one. You can do 2 things. First of all, you look at the points where the points are given. One point was here in subsection here, away from the force. There was a point A here. I believe there was a point B there. Is that correct or not? And they have given you the strain at those 2 points, correct? And they are asking you to calculate the value of P and D. Now, let's forget about that. Let's say P was given. If the P was given, you go to the basic idea. Are you paying attention, please, there, back there? Is if the P is very important. People do lots of mistake here. 2 things. One is the static part of it. The other one is the strength part of it. Now, you can do 2 things here. You can change this force P from this location to that location. When you do that, you are not using equilibrium. You are using equivalent system because these are external loads. This has nothing to do with the internal load. And you learn in the static, if there is a load here, you want to take it out from here, put it here, you have to replace it with a force and a couple. So that indicates where your direction of your moment is. However, in most cases, you don't need to do that. You keep the load there. Then you go to this cross-section. So you go to this cross-section and make a cut there. And as we did it in many homework, including the homework number 1, you come to this section. What stresses is about what's happening in this section. Yes, sir. And that section with this force must be in equilibrium now. Everybody understand that? So here I'm going to do the equilibrium. So this is point A, this is point B. Obviously, this is the neutral surface, so this will be the neutral axis there, correct or not? However, we said it many times, everything has to come to the centroid. You cannot keep it there. You have to bring, because if I want to use lecture 1 or 2, the chapter 1 and 2, lecture 1 and 2, force has to be at the centroid of the cross-section. Therefore, your internal force turns into this force. Now, this system, this piece has to be in equilibrium. Otherwise, it's going to fly. Is that correct or not? Yes? So therefore, whatever you put here, which is, we call it normal force, that normal force, which gives you sigma equal to force over area, chapter 1 and 2, that is at the centroid, must be equal and opposite now. Notice this is different from what you were doing there. So this is internal, that is external. Be careful about it. We are going to use the same system here for the shear moment diagram. We have external moment and we have internal moment. We have external action, we have internal action. External is the static, internal is the strength of material, is all about. Now, is this in equilibrium? As far as the forces are concerned, it is. As you see, it is a couple, yes or no? Therefore, the action of the couple is like that, yes or no? You need to balance it, obviously. Very good. So you have an M here. Now, this is what we are talking about in the strength of material. This sigma and that sigma has to be added to each other, yes? Alternatively, you could have replaced this force also with a force and a couple. But when you do that, you are not using equilibrium. You are using equivalent. That's why some people get the sign wrong. So in that case, if I want to bring this, take it from here to here, which is the equivalent system now. First of all, I put the same P there. Then since this was pulling it up, so I have to pull it up and push it in. Everybody said, don't look at it there. And this would be your M, which would be equal to P times. Now look, the system is in equilibrium. But there is two options there. One, to change the action, take it to the centroid, or forget about it, go directly to the body of the material and the maroon one. The maroon one will now give you the stresses. This is one question. The second question is what you were asking that. Many people, they don't understand this part of it, or they don't know it. Many people do. I had this question from the other class. They said, I don't know, I used plus, didn't work. I used minus, it works. I don't know what's happening. Now, what's happening is this, that in solution manual, they are using sigma equal to minus my over I. Yes or no? Yes, that's what they do. Some students do that, but they are not probably hearing. I know that for a fact because I know they are copying it. Is that understood that? But then they get confused for the sign of it. This one, there is a sign associated with that. But I ask you, do not use that. If you want, you can use it. There's nothing wrong with that. It's perfectly okay to use it. But look here. I don't need any of those signs. If this is point A due to this one, due to the P or actual force, this is, let's write it here. Forget about that, write your sigma here. There is a sigma A there, there is a sigma B there. Is that correct or not? Now, forget about the moment due to this force, everything is in tension. So you put here N over A or P over A, so because N is equal to P over A, and you put P over A. Here, correct or not? Now, here, look, forget about that formula. This formula here is what? This is, look at this. This is in tension, this is in, that's it. Forget about sign and everything. If it is tension, I have to plus, so here I have to put plus M y of A divided by I. It is in tension. This is in compression. I have to put minus M y of B divided by I, and I believe A was given, I thought this was a little bit lower, I get the A was given equal to 15 millimeter and B was given at the distance of 30. Now, some people looked at and they try to use that. That one is associated with this system, guys, so please be careful. First of all, they are assuming Y above the neutral axis is plus, Y below the neutral axis is minus. And then also there is an M there, which is correct. All of them is correct. This M is positive. Everybody understand that. When M is positive and Y is positive, this automatically become compression. Everybody understand that. But then here you have to use Y negative, so you have to assign signs. So in other words, if you are using this formula the way they are using it in the solution manual or in the other example, they use this formula, but Y has a sign. So if you are above the neutral axis, 15 is plus 15. If you are below, you are up minus 30. So you follow all, and this M is plus, and this M, remember we talked about the shear and moment there, and that M is minus. So you have to follow, but none of them is needed as long as you draw the diagram. That's it. So why do you want to do that? Is that understood that? So look what happened. So if this M become negative, now Y here is positive, M is negative, negative times negative become positive, so it is tension. But you can look at it. Why do I need that? Here is tension, here is compression automatic. Just to look at it, you see that. Everybody see what I'm talking about. So many people or several people in the other class, they were using the solution manual, and they said, well, it did not happen, but I changed my sign from minus to plus. I got the answer in the back of the book. That means they didn't follow the rule. Everybody understand that the rule is very simple. Draw your free body diagram correctly. You see where is tension, where is compression. You don't need to use that, although that's a correct formula. Everybody, the correct formula, assign sign both to M and to the Y. You have to assign sign plus, and if M goes like that, it's plus. M goes like that, it's minus. Above the neutral axis is plus. Below the neutral axis is minus. So if you are using those formulas, do that. Is that clear for everybody? Yes? Okay, let's move on now to, because this problem, at the end of the problem, I'm sorry. The rest of this problem, let's put it back. The rest of this problem was like that. Since P was not given, instead, epsilon was given here. So of course, I explained that in class in another example. Since epsilon was given, and epsilon equal to sigma over modulus of elasticity. So in effect, sigma A was given, sigma B was given. Your two unknown was P, M, but M was equal to P times D. So it became two equation and two unknown that you had a little bit of problem how to solve that two equation. The best way is to subtract these two. Just multiply this by a number because this is the same, this is the same, this is YA, this is VB, so one is twice as much the other one. Multiply this by 2 and then add these two. These two become eliminated immediately. That's the best way to solve that. So many people don't use that method. Is that correct? Don't use the method in the book, by the way, solution manual. It's confusing. Did you see what I did? Yes, multiply by, this is always the best way to solve two equation and two unknown. Here, look, because YA is half of YB. Everybody see that? So if you multiply this by 2, all term, and then you add these two together, this and this become eliminated, you solve for P immediately. And after you solve for P, then you put it there, find M, which is equal to PD. Anyhow, that's the easiest way to solve this problem. Now, we are going back to question in hand, which is shear and moment diagram. Now, I want to give you the balance of everything that we have to know. Now, you guys must remember everything I said last Tuesday. So anybody who was not present here most likely will not understand what I'm doing here because everything is connected to each other. Without those ideas that I presented to you, which one was the integration? Remember, one was the integral. The integral of the shear was the integral of the load was shear. The integral of shear was moment. One way we go integration. The other way we'll do the derivative. That defines the shape of shear and moment diagram ahead of time. We know that. Secondly, these are the key questions you want to answer. I'm going to show you today, especially because I'm going to do one more very complex more problem which covers all your homework. Everybody understand with one question only because that's all the time I have. Now here is, I call it the static method, the static / equilibrium method, which basically I used last time to draw my shear and moment diagram. Then there is another method which I'm going to do it today. As you will see, it is very easy. We can quickly establish that one, which we call it area method. Bless you. He has hay fever. Allergy. I have a little bit of that, but I take pill for that. Okay, so therefore, that's the same. Now, there is another method that they are using in the book, and since we have a little bit behind, I'm going to eliminate that. Sometime I talk about it briefly, and anyhow, in any other class, be careful here, by equations. Now, here, I briefly show one of the equation in one of my examples. You can draw the equation, you can write the equation of the load, then integrate that to get the shear, then integrate that to do the moment. That method also is applicable to all our problem. But I'm asking you not to use it. Everybody does. If you use that and copy it, write it down in your note from solution manual, you are going to either 50% chance that you may be correct or may be wrong. First of all, your knowledge is limited to that. In that method, which is a very logical method and very direct method for all this problem, is going to be discussed for all the mechanical engineering. It's going to be discussed in ME 219. Actually, we are going to spend 2 weeks or a little bit more in that method, which is, we call it integration method, which is the general method for all the other problem as well. Everybody understand that. However, there are much detail there. There are boundary condition there. There are support system there. There are single load, single moment coming to the picture. At this time, we don't have time to discuss all of that. So if you are using integration method, you are not 100% there. Therefore, most likely you are going to make mistake. Everybody understand that. So I'm suggesting that for you not to use that method. Occasionally, I have asked a student to write the equation of the shear and moment, but I'm going to bypass that for this quarter as well. Is that understood? So that method, if you see it in the solution manual, please do not copy it. And if I see that you are using that method, you don't grade it. Concentrate in these two methods because that's all the question will be like. And that's the basic, because you need to understand that in order to understand the integration method as well. Is that understood? That yes? Okay, now going to show you that static or equilibrium method, I'm going to put here another problem for you guys. This is a new problem. It's unfortunately not in your handout. So please draw the picture there, and I'm going to draw the shear and moment diagram for you. Here is the beam itself. So it is a shorter beam is going like that. At certain point here, so let's see down here, there is a sort of hanger here like this. The beam is there. And there is a force of 400 pounds hanging here. This is a pin here, a roller there, and there is a load of uniform load of 40 pounds per inch, and the distances are following. This is A, this is B, this point here is C, this is D, and this is E, and we go like that. This is not in a scale again, sorry. This is 12 inches from A to C, 6 inches from C to D, and 4 inches from D to E, and 10 inches here. I purposely do it this way because this, as I said, is a little bit more complex. Which is near the end, you get this kind of problem. Yes?
What's the distributing load again?
40 pounds per inch. Like a weight sitting there, you're putting a weight, 40 pounds. A uniform load of 40 pounds per inch. There are the seats over there probably. I'll come over here for the rest of it because I need all the board here to show. Is that correct or not? Yes? All right. Now, first thing first is, guys, when you do such a thing, remember what I just told you. Everything has to go to the centroid. Yes? And this load is not at the center. However, by putting it here, still you can calculate the reaction there and reaction there. However, I would suggest you move this point from E to D and take it to the centroid. Everybody understand that? Because that was the idea I just showed you in the other one. Everything has to be there, correct or not? So here, this is equivalent, static equivalent to that load, which I'm going to put it here. So we have here, again, a uniform load, 40 pounds per inch, I'm sorry. And then this is point D. We don't need the point E now. So here it is. This is 12 inches, this is 6 inches, and this is 14 inches. Now, and of course, I have here the support. Now, support here, I have, you can call it AY or RY, doesn't matter. You have here RBY or RB, the reaction. There is no horizontal reaction here because there is no horizontal force, yes or no? Now here what we are going to do, we are going to take this 400 to put it at D. I just explained that you purposely. So this is not equilibrium, this is equivalent. You are changing from one force from one point to another point. You need to add a couple to it. Is that correct or not? So this is understood that load, exactly what you learn in a static. The load goes itself. But look at the couple, which way is moving? Look at that. Put your hand here. It is going like this. Is that correct or not? So there is a moment here or a couple there. And this is your MD externally. These are all, again, it's the external. The idea is to find the internal one. Is that correct? Which is the shear and moment diagram. Remember that. The internal one. So here is MD. But what is the value of MD? Look at it. Of 400 times 4 inches, so MD is 1600 going that way, clockwise, and it is pound inch of moment there, and the force itself, of course, is 400 pounds. This is equivalent to this, nothing wrong. Both of them are acceptable to calculating the reaction at A and B. Next, I'm going to bypass that for lack of time. Next is to calculate the value of AY and BY by static, which taking moment about here and here. A warning. I gave this problem to ME218 for a beam with integration method to do lots of other things beside what we are doing here. Many people, when they took the moment about here, they didn't put that M into the system, everybody, because the M was here, and they forgot to put it there, so all their reaction was incorrect. How can they do that? I don't know, because I really didn't like that. Everybody understand this is something as an engineer you cannot do. Is that correct or not? So M come into your picture, affects your, in other words, M pushes this one. If there is, I want you to understand this. If there is a beam like that and there is a moment like that, people think there is no reaction here and there. If this one actually pushes down, so you have a reaction here going that, but this one will be a reaction this way because it wants to go up, but these two are equal, and because there is no, they don't see any force, they think there is no reaction. That's their idea. Is that understood there? So a moment create a reaction on both sides, equal and opposite. So if this moment was not there, so the reaction would have been different. Is that correct? Yes.
How would we get 1600 for the
What?
moment of D?
Excuse me?
How'd you calculate 1600 for the moment of D?
How did you calculate that? It's here. Because I moved it from here to here, this distance was 4 inches. Okay? All right. Let's take that one over. So this is now understood. Now, based on taking moment here and bringing that into the system, you calculate, I give you the idea. The total load is 40 times to a 480 plus 400, so it's 880. You can write sigma Fy. Anyhow, this becomes 515 pounds. And I have the answer here, so you don't have to worry about it. We are bypassing that. And this one becomes 365 pounds. Is that understood? Yes. So I'm going to erase now this one totally because we don't need that anymore. So, but these are point A, B, C, and D. Okay? Now we want to draw shear moment diagram quickly using this static method. All you have to do, find shear and moment, shear value and moment, write it down at point, write it down in your note. All you have to do, find the shear and moment value at A, C, D, B, and connect that together, which is very easy. Is that under? And this is what we call it a static equilibrium. By the way, this problem, what does it say here? Problem number 1. 7 point, it is copied from your static book, the one you were taking. Do you remember the static book Johnston we had? Remember we skipped chapter 7 in a static? This is out of static book. That means this idea should be part of static. And it is. Next quarter, one of the things we are adding to a static is this shear and moment diagram. It has nothing to do with the strength of material. It's all about equilibrium. Everybody see that? So let's start with the shear diagram. Okay, shear diagram, as we said it before, you draw a line here, X. You put here shear force, and you declare your unit. In this case, unit is pound. And you start with that. But I hope you haven't forgot everything that I mentioned last Tuesday. What's the shear value here?
0.
Nope. The shear value is 515. Probably you missed that. That's correct. 515. Is it plus or minus? Plus. Everybody with me? The force, because you have to put your, again, if you have forgotten, go to your handout, put your sign convention in front of you if you have forgotten. But this is something you should remember. You said in the final, I'm not going to give you the sign convention. The sign convention is something you should remember, like sign convention for a static. Everybody knows that. This has a sign convention of its own. Everybody understands, because there are two forces, two moments always. Is that correct or not? However, just a reminder, since this is going up and this was going down, that format was a positive format, we call it. Therefore, start at 515. So that's the shear at point there. We had it in other problem there. Then afterward, notice the load is, you are here. Other than you be 0, you are at this point. So forget about that. After that, I have to take care of that. But this force is negative. The shear as the result of that is upward, which is a negative format. Yes or no? If it is negative format, I should be going down. I should not going up. But am I going down? How? Remember again, if this is constant, this is linear. Why it is linear is obvious there. If I go 1 inch, it's 40 pounds. If I go 2 inch, it is 80 pounds. You see, it's there. It's sitting right in front of you. You have to think about it. And then you go 3 inch, it will come. So on. That's a linear format. Is that correct? It's 40 times distance, correct? So therefore, you go linearly, but you don't have to worry about 1 inch, 2 inch. Actually, I explained that in one of classes, old classes, 5, 6 years ago. And one student was doing it for every inch. No, you don't need that. All you go to point C. If you go point C, how much should you subtract? 480. But then you should go linearly. So you are at 515. We should reduce it by 480. What do I end up? So you see, you right away write it here. Shear at C, so is equal to 515 minus 480, which is 40 times 12. Is that correct or not? But linearly, so it becomes 35 pounds. So you must go at this point. You will end up for, you just put it here, 35. Is that correct? The unit is sit there. Is that correct? As simple as that. Notice I'm explaining it to you, but if you really were doing this by yourself sitting and you knew the idea, you would do it less than 1 minute. Is that correct or not? Then what happened afterwards? Is there any action happening here? So therefore, I must go between here to there. I have to go constant, yes or no? However, something happening at D. Look, there is a point here I made last time. I'm again refreshing your memory. You should be at D minus and you should do at D plus. I hope that's not your grade. D minus. I want everybody to get A minus, A minus. So there is a D minus and there is a D plus. Everybody understand? There is a difference. Right now we are at D minus, yes or no, which you are here. As soon as we pass that point, there is a 400 change in the value of the shear, yes or no? The only question, should I go up or should I go down? Of course, I have to go down because this is down. The action here afterward is upward. That system is negative, so I must be going down. So as soon as I get here, I drop it 400, so I got to minus 365. So here you write for me, if this is your quiz, this is how you should represent to me that you know everything. So shear at D minus is still 35 pounds. Shear at D plus is equal to 35 minus 400, so it is minus 365 pounds. We are just doing this by inspection. We are not using any formula or any equation. And you end up F. So what happened after that? Notice moment does not change your shear. The shear is about forces only. Is that correct or not? Then nothing happening until point B, and at B I have to go up 600, so I end up back to 0. So after you go past the beam, the shear is 0, but an epsilon before B or B minus, which is a good grade anyhow, B minus is minus 365. Everybody understand that? Which means if I want to draw the shear there, so now if this is the section, I cut it like there. This is the section B, right there, I'm cutting it. What do you think this shear minus looks like that? Minus means this side should be going up, this side should be going down. That was the minus. You remember that? This is not a static plus or minus. This is according to that sign convention. Again, look at your sign convention. I put it in the board last time. Remember that? Okay. So therefore, that's how it would look like. But we'll talk about it in chapter 6. Because when we go, now, by the way, the stresses due to do this will be in chapter 6. Remember that we have not yet touched that one, so but we go there. But now we are talking in chapter 4, we were talking about moment. Now I have to draw the moment diagram associated with this loading. So this was it. But remember, this part of this, I'm going to erase that. This part of it is plus. This part is plus, and that part according to the sign convention again. Okay. Now I have to draw the moment, which I'm going to put it here for everybody. Can you see it from that side? Or yeah, because I need that board for the next subject. So here we go there. Moment diagram, guys, like that. You put here an X there. You put here a M and pound inch here. And then we go like this. Of course, this is a external pin. There is no moment here applied there. So the moment at that point is equal to 0. Yes? Now, how the shape of the moment should be between A to C. Remember, we have a point C to worry. We have a point D to worry. And then at the end, we end up with B. Is that correct? So you put those points down. Now, this is what I talked about it last time. This is constant. The load is constant. The shear is linear, the line, average is that, and then the moment is a parabola. From here to here, it should be a parabola, but remember, the parabola, some of you may ask that question, but I'm going to answer that next week or at the beginning of the next class, because that's a little bit, we go through this, then you will see what happened there. It may go like that. Everybody, all may go like this. Is that correct? But let's leave it at that for time being. Let's go like that. Is that correct? There is a reason for it, but reason of that is all about integration. Some of you may already guess it, but I will explain it to you later. Is that under? Let's finish now based on the equilibriums. All I said, make a cut at C, yes or no, and find the internal moment and shear at that point. Yes. So all I have to know, the shape of it is a parabola, and I want the value at that point. Everybody see what I'm talking about? That point is at point C. All I have to do, make a cut here at point C and draw a free body diagram. This is that free body diagram. This is all a static equilibrium based on the cut and free body diagram. Here is, write it down, 515 pounds. This is 12 inches. It's been loaded like that, a uniform distributed load of 40 pounds per inch. Now what I should put here? Now, what I should put there, it would be a shear at C and a moment at C, because that's point C. Notice that's not point X, everybody, the way I did it last time. That is the value of the shear at point C and moment at point C. Now, my point is, should I put my shear upward or downward to indicate it is plus? Remember, this is the plus, this is minus. I'm not talking about the static. I'm talking about the sign convention. If I want to assume it is plus, should I put it up or should I put it down? Down, absolutely, because that was your shear. Remember, this was what we had. This is positive in there. You are here, so you should put it down. Although, granted, that's statically is negative. That's not the point here. The beam should behave like that. Is that correct or not? Therefore, remember, this was in your first homework. In your first homework, when I asked you to do the shear and moment internally, some of you asked why all the shear, they are putting it downward, not upward, because at that time you were thinking static. Now you are thinking shear and moment diagram. That's why they put it downward. Is that understood? Statically is negative, but that's the deformation-wise, it's positive because it's deformed like that. So that is shear at C, and that is moment at C. Again, moment should be like that because I want to put the moment in the smiley face. Everybody understand? Yes, that's the whole point. However, you draw a free body diagram from the other side and you are putting it here, your moment should be like that. Everybody understand what I'm saying? That again, statically this is plus, statically this is minus, but this is the same as here. Everybody see it? This is the right hand side, this is the left hand side. So if you are seeing in the book again, they are using the other part of a beam, they're putting it this way, don't panic. This is the same thing. Is that understood what I'm talking about? They are using the sign convention for, this is the sign plus sign convention for the moment. This is plus sign convention for the shear diagram, which are the internal, not external. External is the static, you just use the static. Correct? All right. Now, saying it all of that one more time doesn't hurt because these are all repeat. But nevertheless, everybody has to get to the picture. So always remember that I put a star last time. I said use the star one. This is the way we do it. Is that correct or not? Now let's write the equation of equilibrium. We are back to static. So everything this way is positive, everything that way is positive, counterclockwise is positive, clockwise is negative. That's a static. Now I'm writing a static. That's why I call it a static equilibrium. I'm using, this is equilibrium, this is a static. So sigma fx equal to 0. That means 0 equal to 0, not going to help me, yes or no? But sigma fy equal to 0, sigma fy equal to 0. Notice this is upward 515 minus how much load do I have here? That is 12 times 40 minus 480 minus, this is downward. So minus that shear, is that correct or not? Equal to 0, or shear at point C become 35 pounds. Notice we already knew that because I did it by inspection. Is that correct or not? Yes? Or if you don't do it, cannot do it by inspection, here is the answer. Is that correct? It's plus 30. So you have to go from 515 to plus 35. Yes or no? Now we can do the same thing for the moment. In order to take the moment, you should never take the moment about A. You should always take the moment about point C. Everybody understands, because you want to eliminate this. Is that correct or not? If you take a moment about A, you have to, don't forget, because I have seen students do that. They take the moment of that and that, but they forget about this one. Is that understood? Yes? So however, take always, this is what we do. Sigma M at or about point C equal to 0. Now I have one more complaint to do, no matter how many for you, and no matter how many times I say it, students still follow that. Many of you, when it comes to this point, I don't know how you learn the static. Rather than the way I wrote it, you write like this. What does it mean? If you write it like that, what does it mean? That means this moment equal to 0. That's what you are saying. Is that correct? Absolutely not. That's not what I said. What I said earlier was this, which is this English sentence, summation of the moment. Not, I even add that. This is, sometimes they write that, still they think this is equal to 0. Everybody, summation of moment at or about point C must be equal to 0. In order to write all that long sentence, we just summarize it in this symbolic format, which is not MC equal to 0. Correct? Yes? Don't get me wrong. In ME 218, there are still 1/3 the students do it that way. I mean, don't laugh. It is in this class happening. It's in the other class happening. It is happening in future. Don't do that mistake. It is so simple. Is that correct or not? Because of the lack of paying attention to the detail. Nevertheless, that means I have to take care of this, and that, all of them. Is that correct? Including MC itself. So therefore, it becomes like that. 515 times 12 plus or minus. This is now static. It's going clockwise, therefore it is negative. Then this is 480 times what? What's this distance? That distance is 6. Is that correct or not? 480, it's very simple, times 6, and that is plus. Is that correct? Yes? Then we come here. Shear doesn't have any moment about here because it's not, but we have a MC sitting there plus MC. All of them said, we had even in this class somebody else asked you, I don't know who was, that did last class. They asked me, I get it. They put equal to MC, wrong again. Summation of the moment about point C equal to 0. That means this is plus MC, then equal to 0. Yes, sir. Correct? To get the right answer. Notice, these are all the action. This is all the reaction that together must be equal to 0. So the reaction become opposite to the action. This is what we are using all the time. So anyhow, that number become equal to, if you calculate that one number, that number ends up to be 3,300 pound-inch. Because this goes to other side. This is larger, this is smaller, so it becomes a positive number. And we know that this number is 3,300. You can put it there or you can put it there. Everybody understand? Yes? All right. Now, what do we do afterward? Be quick later, otherwise we cannot finish this. From C to D, what should I do now? Come on, guys, give me some hint. Is it going to be a parabola or going to be a line? Line. Should I go up or should I go down? Now, here is the question. Look, guys, this is, just use your intake. This part is plus. What is the integral of a plus? Plus, yes, it's not minus, yes or no? So the integral of plus 5 is plus 5x. Is that correct or not? So I should be going up, not down. Is that correct? I'm using the integration idea, but I'm not using it as a formula. I'm using as, so therefore, must be going up. How much up? Even if you don't know that, you are draw another free body diagram for D. This was the free body diagram for point C. Let's draw the free body diagram for point D. Although I know it's going to go up, but if you don't know that, so forget about that one. Although I'm going to show you the second method which defines that as well. So therefore, this time I'm going to, well, some people draw this, they try to draw the free body diagram of CD, which is totally wrong. Because if you do that, you have to put all the internal on both sides. That's not what usually we do. We draw the free body diagram from A to D. So make a note of that one. So we extend that. This is point C. We extend the beam all the way to D. And this is 12 inch now, and this is 6 inches now. Is that correct or not? Yes. This time we are going to put there the value of shear and moment at point D. That's all we need, and the problem is finished. So here we put shear at D and M at D. Is that correct? That's all I said to do in method 1. Calculate at C and D and connect those points together. Is that correct or not? Yep. Okay. So what do we get this time? So I do it in blue. Sigma Fy equal to 0. This time, notice we have 515. I don't have to do it. Minus 480. Nothing else added. Minus shear at D. And therefore, equal to 0. Shear at D become, again, the same 35 pound. Notice we had done that by inspection. At C was 35. At D was 35. Everybody with me? Yes? Now we need the MD, because that was the only question. So to see whether it's going up or down. So sigma M, again, at point D equal to 0, like before. This time we have 515, not times 12. 515 times 18, negative, that's 18. And then we have 480 times this distance from here, which is 6.5 of 12, which is 6 times 12, correct? And that one is plus, nothing else added, plus MD equal to 0, and MD ends up to be equal to 3,510. As you see, it has increased. The indication was there because the shear was, because remember that we said this is integral, moment is integral of the shear. The shear value is positive. That's what I was saying that. So the moment should be positive. I knew ahead of time it should go up, but if you don't see it there, do it there. Look at there that it has gone from 3,300 to 3,510, 210 extra. Is that correct or not? Yes, but it is a straight line. So you go to D. Of course, this you don't know how it goes, but I would talk all about that if I have. It should be tangent, but you don't have to worry about that. So that value now is, I'll put it here, 3,510. The unit is poundage. Is that correct or not? But that is the value for D minus. Again, this is, let's put it here, D minus. Everybody understand what I'm saying? Now, here is the one that many students miss in the final or in the homework. Is this moment value is going to change from D minus to D plus or not? It's obvious. It should change, like the force. There was a force, you change the shear diagram. There is a moment, you should change the moment. What's the value that changed? That's how much is going to change. We are right now at when we are an epsilon before, which this doesn't show up yet. Here the value is here. After I pass that, I have to change it by, obviously, 1,600. The question is this 600 plus or 600 minus? That is 600 minus. So I should be going down here. Yes? Yes? No. Is this internal or is it external? Aren't you looking for internal? Yes or no? Yes? Okay. So that's the irony of that. You have to remember the sign. If I have an action like that, what kind of reaction do I need to balance that? This, yes? Is this plus or minus? Which one is that? If you have an MD sitting there on externally, beam going to, this is action, this is the reaction. Everybody understand? Exactly matches that. Is that correct? Your action is negative, the reaction is statically positive, therefore I should be going up, not down. Everybody see that? Because that system is positive. In despite what you were thinking, everybody, because you see that you're still living in a static. Get out of a static, go to the sign convention. Is that understood what I'm saying that? If you have a piece of beam like that, you have this. Is that what you have 1600 there? Yes or no? After the action comes afterward. Yes, so you need this to balance it. What is this? Is it a smiley face or frowny face? Therefore it is plus. The beam is going to go like this, not like that. In other words, the beam is going to go like this. And that is a smiley face. Yes? Correct? If the action is like that, the reaction is that like, that's where it goes frowny face. Yes or no? This is negative. This is positive. That format is positive. Look how much information goes there. So I'm not going to go down here. I'm going to go up 1600 to write that. So it becomes 5110. Please write it down. Now, if you didn't understand it, all you have to do, draw another free body diagram. This time I'm going to add it here. So I'm going to go D plus. That means now these things appear there. Is that correct or not? Yes? In that format. This is definitely statically that is negative. Look, but when you put it in this equation, this remains the same, this remains the same, this becomes MD plus, yes or no? However, is this plus or action-wise? This is equal to minus 1600, correct or not? Yes, but look, MD is here. This has to go other side. Minus become plus, so adds to it. Is that correct or not? Everybody see it again. This is the action. This is the reaction. So add it that. Look, guys, I'm writing one more time, putting this in system. What's the moment at that point? 515 times 18, correct or not? Negative. 480 times 12, positive. Minus 1600 plus MD. Is that correct or not? That's exactly what I've done. Minus 600 plus MD. But when MD, this goes to the other side, minus become plus. Therefore, the moment increasing, not decreasing. You can see it by equilibrium. You can do it by sign convention. Either way. Everybody understand that? Yes, one more time. This requires plus. This requires minus, and we have this format right now for that beam. Anyhow, that is the one you have to be very careful there. And from then on, nothing else is happening there. Because from then on, from here to here, I have a line. And moment here is 0. Therefore, I draw a line from there to here, a straight line. And that is your moment diagram is finished. Everybody see that? Yes? OK. Notice if you draw the free body diagram for D minus, you shouldn't put it there. For D plus, you should put it there, and all of that will reflect that.
What did you get the 1600 again?
1600 was the value of MD. If I want to put that MD here, the value of that is, that was the whole question. Is that correct or not? Yes?
So I know you weren't going to talk about the integration, but if you integrate the slope of the shear, that'll give you then the max value for
Yes.
the...
Yes. Not always, though, but because there are about anytime this comes into the picture, you have a problem there. So that's why I don't want you to use. Yes, absolutely. So which I'm going to do it right now in a different format to show you what the area method is. Absolutely, you can do that, but I'm not suggesting for time being because I'm going to do that for my classes next course semester. 2-3 weeks we are going to spend. Right now we just finished it in ME 219. We have spent 2 weeks and a half in integration method. Because that leads us to computer programming, that leads us to finite element method. That's the basis of all the real stress analysis of real structure, everybody. But we start from there and move on and on and on. But just wait until we get it in all the detail. When you do something, just a little bit of it, not the whole thing, you get the wrong idea. Sometimes you make a mistake. That's what I'm suggesting. Wait until we get it done right. That I give you all the detail. It takes 2 weeks to explain all of that. But anyhow, now remember that. I said this is very important to remember. I said W, when we integrate W, we get the shear. And when we integrate the shear, we get the M. Is that correct? Or vice versa, if I have the M, I take the derivative of M, it becomes shear, and derivative of shear become W. That's what we are using here. Remember that. This is, again, this is constant. This is linear. That is parabola. No load here. Shear is constant. Moment is linear. Everything that I did that was based on that formula, which I gave it to you last time. So that's very important, which is based on the integration as well. Actually, the slope of that curve is based on the integral. You already saw, some of you with good at calculus, you already saw whether I draw it this way or that way. That's all, see, because this is the rate of increase, keep decreasing. Now, this is this. As I go down, I'm adding, add, but I'm decreasing it. So the slope of this curve should be decreasing. If I go this way, the slope keep increase. This should have been like that, then I would go that way. Is that correct? So this is all static based. Whether we do need all of this or not at this time, that's the question of time. Is that understood? Yes? But all of them. Now, this is what we are going to do. Since derivative of shear with respect to x is w as a x, is that correct or not? Derivative of that one with respect is w, correct? That's what we are using there. Therefore, this can be written in this format. Derivative of dv become equal to wx dx. Then I integrate that between two consecutive points, which we call it c to d, c to d. Now, integral of dv, of course, become shear, and shear has to be evaluated between c to d, so we write it at vd minus vc equal to, what's this? Integral of fx dx. Everybody knows that in calculus. What is that? That's area. Fx dx is always the area under the curve. Is that correct or not? But since it is w, must be area under w. Is that understood? That? So we call that area, write it down, area under load from C to D. Similarly, for moment, we do the same thing. So again, derivative of m with respect to x must be equal to shear as a function of x. Is that correct or not? Therefore, we write dm equal to vx dx. Then again, we integrate that between two points like this. This side, left side, become m. Integral of dm is m to be evaluated between these 2 points. So it becomes md minus mc. This side is what? Is area under the v function, yes or no, or shear function. So you write it, area under shear function from C to D. This method is called area method. That's what I'm referring to that. All we have to do, calculate the areas. If area is plus, we go up. If area is minus, we go down. Let's see whether it works, because I don't have time to do another example. Let's see whether it works for this one or not, which that's what I kept the picture there. Everybody see what I'm talking about. I'm now using the area method, not the other method. First of all, let's assume, first of all, this area method is not good for shear, because the shear can be done by inspection. Notice that the shear diagram is very simple to do. So I suggest you always use it for moment diagram, which is simpler. Is that correct or not? Look, this is what we are saying, that C and D is arbitrary. So I'm at A and C. Everybody see that? C versus A. At A, I have a moment of 0. At C, if I go to my shear diagram, take the between A to C, this is A, this is to C, I need that area. Is that correct or not? That's the area under shear function from A to C. Now, everybody, without any exception, take your calculator. Let's say this is a quiz and you want to do this problem quickly. You want to calculate that area. So what's that area equal to? Here is 35, here is 515, and the distance is 12 inches. So this is what you should do. If you are doing this method, not the other method, you are showing me the free body diagram, sigma f, sigma m. In this method, you have to show specifically. If you don't do it, I don't give you any credit. Don't copy this, in other words, from somewhere, put it there in your final or in your quizzes. You need to specify what you are doing and tell me what method you are using, either free body diagram or that. What's that number? What did you get? Come on, guys. Everybody should do it. That's 35. I mean, you don't have difficulty doing that. This is 35. 5/15, average it, 5/15 plus 35 divided by 2, multiply by 12. That's the area of a trapezoid. What did you get? 3,300. I give you answer ahead of time. 3,300. Yes. So you go from 0 to 3,300. Look, that's what the number is. We did it for free by a diagram. Now this time we are doing for, you are going to love this method, but don't use it always. This method is good if your shear diagram is good. If your shear diagram is bad, that method doesn't do you any good. That's why I suggest you learn both methods. If I were you, I was going to use all my first 4, 5, 6 homework in the first method. Then later on, when you get good at it, then you use the area method or double check it. Let's put it this way, because I will not rely only on the area method. So this area is 3,300. So here was 0. I have to go a parabola. I end up with 3,300. That's why I said this is a plus. No, from here to D, I have to add this much. Yes or no? Calculate that area. That's area of A2. First of all, that's plus as well. That's 35 times 6. So obviously, that is 210. You don't have to calculate 35 times 6. That's 180 plus 30. That's 210. Yes or no? So how much do we add to that? 3,300 plus that area, which is 210. That is 3,510. Now, I have given this problem. People like the area method because they think it is simple. Then they don't do that. From there on, they use the area method. Everybody, which is wrong. Everybody see what I'm talking? At that point, you have to adjust it by 1,600, which has nothing to do with the area method. Everybody see what the point I'm making there? So you have to go from there to make this adjustment because of that MD, which was 1,600. So you have to go up 1,600. Then I have to use this area. Is that correct or not? Now calculate that area. That area of area 3 is actually negative. Yes or no? Correct? What's that area? 365 times 14. Is that correct or not? And that should be equal to 5,110. You are here. You are subtracting. That becomes minus 5,100 pound-inch. So you're going from here to here. You are done. I use this area. See how quickly this can be done, guys? You need to practice this. Now, go to solution manual. You see these two pictures. Copy it in your homework. You are getting 0 value out of that. Everybody understand that? You can do that. I have no objection to that. But are you going to be able to do all your quizzes and homework? Or as an engineer, are you knowing all of this? No, not at all. Everybody see that? How much time do we have for quiz?
14 minutes.
40 minutes before we have time?
To do the quiz, it's 10,
To the-
15.
Oh, it's 10:15 right now?
Yeah.
So I have no time
No
there.
time.
Oh, that's what you are saying. Okay then. Okay, we leave it at that. So.